Are you curious about what occurs within your body when a drug is injected directly into your vein? In this video, we'll dive into one of the most important topic in pharmacokinetics, that is one compartment open model with IV bolus administration. One of the simplest and most significant concept in pharmacokinetics, biopharmaceutics and pharmacokinetics, BPPK. So this will be the equation. Don't worry about it. I will try to explain it in detail. So stay with me till the end of this video. The one compartment open model represents the body as a single or uniform unit where the drug distributes instantly, throughout the body after entering into the bloodstream. The term open indicates that the drug can enter and exit both from into the system. The drug has ability to enter and exit from the system, so it will be known as open model. This model assumes that no barrier okay no barriers to drug movement, and equilibrium between plasma and tissue is maintained instantly. So we'll discuss what is written here. The one compartment open model is the simplest model, which represents the body as a single kinetically homogeneous unit that has no barriers to movement of drug. The final distribution equilibrium between drug in plasma and other body fluid attained instantly and maintained at all times. The term open indicates that the input and output are unidirectional and that the drug can be eliminated from the body. Let's break it down in the diagram. That's our drug is here. So we are inputting it in our system. Here the absorption takes place. If we are taking it in oral form, then the absorption takes place. So we represent it as Ka. Absorption will be represented as Ka. The absorption rate for non-IV routes, Ka will be there. Then what happens after absorption? It where the drug gets distributed in blood and other tissues of the body. So distribution occurs. After distribution, elimination occurs. Elimination through metabolism or excretion. Excretion. Metabolism can happen after distribution. Metabolism or excretion can occur. Since IV bolus is injected directly, so Ka is ignored and only Ke is considered. Ke is the elimination rate constant. We'll discuss about IV bolus later. First, this is the overview of one compartment open model. So one compartment means we are considering body as a one compartment. So our drug enters, absorption can occur if it is oral one compartment. If it is IV route, then no absorption will be there. So direct elimination. Elimination means metabolism and excretion. So this is the overview of one compartment open model. Then we have the one compartment open model is generally used to describe plasma levels following administration of a single dose of a drug. One compartment open models are how many types? IV bolus administration, continuous IV infusion, extravascular administration. In extravascular, we have two forms: zero order absorption and first order absorption. So this three we have to discuss. In this video, we will discuss about IV bolus. In IV bolus administration, the drug is injected quickly into the vein. Okay, it takes only about 1 to 3 minutes for the drug to distribute completely. So we assume that absorption is instant and we neglect it. Okay, then the drug starts getting eliminated. So it gets eliminated by the following first order kinetics in most cases. So as you can see in the diagram that our drug is directly injected into the vein, means it gets into the body, then absorption will be there or not? No, there is no absorption because it is IV bolus. So in IV bolus there is no absorption. Directly we are injecting it, the drug is injected into the vein. So no absorption, direct elimination means distribution and metabolism and excretion will take place. So Ke will be there. No Ka, no absorption rate constant. Only elimination rate constant will be there. So the general equation or expression for rate of drug presentation to the body will be dx by dt. What do you mean by dx by dt? Dx by dt means rate of change of drug concentration with respect to time. Okay, change of drug concentration, rate of change of drug concentration with respect to time. What it will be? Rate in. Okay, we have to minus rate in minus rate out. Okay, so rate in, what it will be? It will be absorption or availability. Rate out means elimination. If we minus both of these terms, we'll get rate of change of drug concentration with respect to time, nothing but dx by dt. Hope it is clear for you. Then since the rate in absorption is absent. Okay, in IV bolus, is there absorption present or not? Only elimination was there. No absorption will be there because in IV bolus we are injecting drug directly into the bloodstream, into the vein we are injecting it. Okay. So rate in or absorption will be absent. So our equation what becomes? Okay, dx by dt equals to only minus rate out will be present. Okay, then we have if the rate out, okay, or elimination follows first order kinetics, okay, what the equation becomes? Dx by dt equals to minus kex minus, okay, as it is I am putting it here, kex, it is the first order kinetics. What the terms are, we'll see here. Ke is first order elimination rate constant. Okay, then x is amount of drug in the body at time t remaining to be eliminated. Okay, and the negative sign indicates the elimination of drug from the body. Now we have got the elimination, okay, elimination rate constant, okay, with respect to first order kinetics. Here we have to estimate the pharmacokinetic parameters. Okay, for a drug that follows one compartment kinetics and administered rapidly, means IV injection, bolus. Okay, the decline in plasma drug concentration is only due to elimination of drug from the body. So the phase is called as elimination phase. Means that there is no absorption. Okay, absorption will be not there, so the drug is drug concentration decreases. Okay, drug concentration decreases. Why decreases drug concentration? Because of elimination only drug concentration will decreases. So this phase is called as elimination phase. Now, elimination phase is characterized by following parameters. First one is elimination rate constant, then elimination half-life, then clearance. We'll look three of them also. First, we have the elimination rate constant. Okay. In exam, you have to write this formula, these equations only. Okay. You have to remember this. If you don't want to remember, I will show you how to get these equations, but it will be a lengthy, so it is better for you to remember this equations only. First we'll discuss this, then I will show you how to get all of these equations by only using this equation. Okay, as the rate of drug presentation to the body is dx by dt equals to minus kex. Okay, this is our equation 1. Then we are applying integration, okay, on the both side. How we are getting, I will show you. Then where x naught is the amount of drug at time t equals to 0. Okay, so above equation can also be written in exponential form. The above equation shows that disposition of a drug that follows one compartment kinetics is mono-exponential. I will show you how to write this. The basic differential equation for first order elimination is dx by dt, which is equals to minus kex. Dx by dt is the rate of change of drug, okay, and ke is the elimination rate constant, and x is the amount of drug in the body at time t. Now our next step will be the, after getting this equation, our next step will be the separating the variables. Now the similar terms will be on the same side. So as we are putting the dx here only, so we have to find the x term, okay, x variable, where it is here x. Here x is in multiplication, so it comes on the other hand, it will becomes in division, so 1 by x. Okay, so minus ke as it is, then dt is in division, so here it will be in multiplication. Now applying integration on the both sides, so we are applying integration sign here and here. So after applying integration, after doing the integration, 1 by x integration will be the integration x, then equals to integration of minus ke dt. We cannot do that because here k and here is t. See, here is x and here is dx, same variables. Okay, so we can do the integration. So here we cannot do. So we are assuming it as constant. We are placing it here. So here is nothing. So we are assuming 1. So integration of minus 1 dt will be the t. Okay, minus ke into d into t plus c. C is the constant, integration constant. Now we are assuming t equals to 0 and amount of drug x equals to x naught. So replace this with these variables. X becomes x naught, as I said, then t becomes 0. So after simplifying, this whole term becomes 0. Okay, only c remains. So integration x naught equals to c. We can write it as c equals to integration x naught. Now we are putting this into this equation. So integration my equals to minus kt. C becomes, okay, c, what is c? Integration x naught, it becomes c. The whole equation is same till here, only the c we are replacing. So after getting this equation, okay, we are rearranging these terms, variables. So in integration x and integration x naught comes to the x side. So here it is in plus, so it becomes a minus. then minus k80 will be the same. Now integration x minus integration x naught becomes division. Okay, integration x by x naught equals to minus k80. Then we are taking the exponential form, so x by x naught equals to e power minus ket. The final equation will be the x equals to x naught goes here, so x equals to x naught e power minus ket will be the final mono exponential decay equation used in one compartment pharmacokinetics. See, we got this equation. So this equation shows the disposition of a drug that follows one compartment kinetics in mono exponential form. Okay. So this all these lines, all these paragraphs you have to write in the exam. It will be necessary, essential, and the examiner will see the equations as well as the paragraphs. But the equations are must. Okay. To that equation, we are applying log. Okay, log. So our equation becomes log x equals to log x naught minus ket divided by 2.303. Because of log, this equation becomes like this. So it is difficult to determine the amount of drug in body X, but it is fact that a constant relationship between drug concentration in plasma C and X, okay, or else since the amount of drug in the body X is equals to the product of drug concentration in plasma C and its volume of distribution. Okay, so it wants to say that amount of drug equals to VDC. Okay, remember this equation, amount of drug in the body X equals to VD into C. Since VD is the proportionality constant, it allows the use of C in place of X. So we are replacing X with C. So our equation becomes log C equals to log C naught minus KET 2 divided by 2.303. This is the slope, this is the intercept, where C naught is the concentration of drug in plasma attained just after its IV administration at time 0. Our equation 6, okay, this equation is in the form of y equals to mx plus c, straight line, okay. So therefore we will get a plot of log c versus t, gives a straight line with slope minus ke divided by 2.303 and y-intercept log c naught. As I said, this is the slope, this is the intercept. So after when you plot a graph, it will be like this or like this. The biological half-life or elimination half-life. So it is the time it takes, okay, it takes for the plasma concentration to fall to half of its initial concentration or initial or original value. So it is calculated by T half equals to 0.693 divided by Ke. Then the half-life is a secondary parameter. So it depends on two things, that is clearance and volume of distribution. So our formula becomes T half equals to 0.693 Vd divided by CLT. CLT is total clearance. The significance of half-life is determines the residence time of drug in the body, then hence it is beneficial in calculating the time at which the drug concentration falls. It helps to calculate the dosage regimen of a drug. An increase in T half indicates an increase in VD, okay, along with the decrease in CLT, total clearance. As it is, T half is directly proportional to VD and inversely proportional to CLT. So the apparent volume of distribution VD is a theoretical concept. It shows how extensively a drug spreads in the body. It is calculated by VD equals to X by C. X is the amount of drug in the body. C is the plasma drug concentration. After IV bolus, okay, after IV bolus, VD becomes X naught divided by C naught. Okay, X naught is the IV bolus dose. C naught is the initial plasma drug concentration at time t. Okay, so and it is expressed in liters or in liters per kg. Okay, coming on to the clearance part. Clearance is the volume of plasma from which the drug is completely removed per unit time. Okay, so Cl equals to rate of elimination divided by plasma drug concentration. Rate of elimination is what we have got dx by dt, and plasma drug concentration is C. So Cl equals to dx by dt divided by C. If we are calculating total body clearance, then we have to calculate like this. Renal clearance equals to rate of elimination by kidneys divided by C. Then hepatic, okay, hepatic clearance equals to rate of elimination of by liver by divided by C. And other organs clearance equals to rate of elimination from other organs divided by C. So the total body clearance is CLT equals to CLR plus CLH plus CL others. So the one compartment open model with IV bolus is easy to understand, yet many students get difficulty in solving these equations. If you have the concept clear in mind, you can easily solve or get those equations. Okay, and this IV bolus one compartment is very important for exam point of view as well as in clinical point of view. Okay, if you found this explanation useful, like this video, subscribe for more videos like this, and make sure you share this video with your classmates.